Okay, this lesson we will learn about the complex number, but before we move to the complex number, we will learn about the irrational equation, where the irrational equation is any equation whether variable is inside the radical. For example, square root 2 or root cubic of 4. To solve, we need to remove the radical first. Example, 3 times square root of x minus 4 equals to 5. We know that the n root of x power of m is equal to x power of m over n. Okay, the 3 times root of x minus 4 is equal to 5 is equals to 3 times root of x equals to 9. Then we divided both sides by 3 and we got root of x equals to x power of 1 over 2 equals to 3. Then it can be written as x equals to 3 square, which is equals to 9. We also know that the x power of m over n, power of n over m is equals to x. So example, we have 3 times x power of 2 over 3 equals to 12. Then we divided both sides with 3 first. Then the equation becomes x power of 2 over 3 equals to 4. Then we multiplied this radix with 3 over 2 at both sides, and our equation now become like this. So the x now is equals to plus minus 8. And remember that ab power of m equals to a power of m times b power of m. Example, 2 root of x power of 2 equals to 4x. But a plus b power of m, it's not equals to a power of m plus b power of m. Example, 3 plus root of 3x plus 1 equals to x. We move 3 to the other side and got the equation like this. And we remove the radix, then the equation becomes 3x plus 1 equals to x minus 3 square. So this will be like this, and got the x equals to x and x equals to 1. Let's check. If x equals to 8, then the result will be equals to x. But if x equals to 1, then the result is not the same with x. So this is only the solution. And we have the assignment here. Solve the equation of x power of 2 over 3 equals to 16. Root of 7 minus x is equals to x minus 5. And the root of 2 times root of x plus 1 equals to root of 3x minus 5. Okay, before we continue to the complex number, we know that the square of a real number is always non-negative. In example given, 4 square equals to 16, and the minus 4 square equals to 16 too. So square root of 16 is plus minus 4. But what about root of negative number? Is it clear that a negative number cannot have a real square root? Then Euler in 1707 until 1783 introduced the symbol of iota for positive square root of minus 1. In example, I equals to root of minus 1. And the root of a negative number is called an imaginary number. Example, root of minus 9 equals to root of minus 1 times root of 9, which is equals to I times 3. Root of minus 7 equals to root of minus 1 times root of 7, which is equals to I times root of 7. So suppose we have I equals to root of minus 1 and I square equals to minus 1. Then I cube equals to I square times I, which is equals to minus 1. And I raised of power 4 is equals to I square power 2, which is equals to minus 1 square, and it's also equals to 1. So to compute I power of n for n bigger than 4, we divided n by 4 and write it in the form n equals to 4m plus r, where m is quotient and r is a remainder so our r bigger than equals to 0 and less than equals to 4. The notation becomes I power of n equals to I power of 4m plus r equals to I power of 4 power of m times I power of r equals to 1 power of m times I power of r equals to I power of r. Example, I raised of power 39 will be equals to I raised of power 4 times 9 plus 3. Therefore, our equation will become I power of 4 power of 9 times I cube equals to I cube, which is equals to minus I. And also to this equation with the same process. We must remember, if a and b are positive real number, then the root of minus a times root of minus b equals to root of minus 1 times root of a multiplied by root of minus 1 times root of b. This will equals to I root of a times I root of b and will equals to minus root of a times b. And root of a times root of b equals to root of ab if a and b are positive or at least one of them is negative or 0. However, root of a times root of b is not equals to root of a times b if a and b are both negative. Now we move to the complex number. A number which can be written in the form a plus ib, where a and b are real numbers and I is equals to minus 1. It's called a complex number. If z equals to a plus ib is the complex number, then a and b are called real and the I is the imaginary part, and written as REZ is equals to A and IMZ is equals to B. Other relations greater than and less than are not defined for complex number. If the imaginary part of a complex number is 0, then the complex number is known as purely real number. And if real part is 0, then it is called purely imaginary number. For example, 2 is a purely real number because its imaginary part is 0, and 3i is a purely imaginary number because its real part is 0. So, we must remember A, two complex numbers z1 equals to a plus ib and z2 equals to c plus id are said to be equals if a equals to c and b equals to d. And let z1 equals to a plus ib and z2 equals to c plus id. That will be two complex number. Then z1 plus z2 is equals to a plus c plus I times b plus d. So the commutative rule, in example, z1 plus z2 equals to z2 plus z1, and the associative rule, example, z1 plus z2 plus z3 is equal to z1 plus z2 plus z3 in the bracket. For any complex number z is equals to x plus iy, there exists 0, in example 0 plus 0i, the complex number such that z plus 0 equals to 0 plus z, which is equals to z. This is known as the identity element for additional. For any complex number of z is equals to x plus iy, exists a number minus z equals to minus a minus ib such that z plus minus z equals to minus z plus z, which is equals to 0. So this is known as an additive inverse of z. So let's z1 equals to a plus ib and z2 equals to c plus id be two complex number. Then z1 times z2 equals to a plus ib times c plus id, which is equals to ac minus bd plus I times ad plus bc. And the commutative rules is z1 times z2 is equals to z2 times z1. And also the associative rules is z1 times z2 times z3 is equals to z1 times in the bracket z2 times z3. For any complex number of z is equals to x plus iy, there exists a complex number 1, in example 1 plus 0i, such that z times 1 is equals to 1 times z, which is equals to z. So this is known as the identity element for multiplication. And for any non-zero complex number z equals to x plus iy, there exists a complex number 1 over z, such that z times 1 over z equals to 1 over z times z equals to 1. In example, multiplicative inverse of a plus ib equals to 1 over a plus ib equals to a minus ib over a square plus b square. For any three complex number z1, z2, and z3, which is z1 times in the bracket z2 plus z3 equals to z1 times z2 plus z1 times z3, and z1 plus z2 times z3 equals to z1 times z3 plus z2 times z3. Let's z1 equals to a plus ib and z2 is a non-zero equals to c plus id. Then z1 divided by z2 equals to z1 over z2 equals to a plus ib over c plus id equals to ac plus bd over c square plus d square plus ibc minus ad over c square plus d square. And let z equals to a plus ib is a complex number. Then if we change the sign of imaginary parts of complex number, then it called conjugate of z denoted by z bar. In example, z bar equals to a minus ib. Remember that additive inverse of z is minus a minus b. No, but conjugate of z is a minus b. So we have z bar equals to z, and 2z plus z bar equals to 2 times real parts, and z minus bar is equals to 2i times imaginary parts. Number 3, z is equals to z bar if z is purely real. Number 4, z plus z bar equals to 0 if z is purely imaginary. Number 5, z times z bar equals to the real parts square plus imaginary parts square. Number 6, z1 plus z2 bar is equals to z1 bar plus z2 bars, and z1 minus z2 bar equals to z1 bar minus z2 bar. And number 7, z1 times z2 bar equals to z1 bar times z2 bar, and the z1 over z2 bar equals to z1 bar over z2 bar, where z2 bar is not a zero number. And let the z equals to a plus ib be a complex number, then the positive square root is the sum of square of the real part, and square of imaginary part is called modulus or absolute value of z, and denoted as z absolute. In example, z absolute is equals to root of a square plus b square. In the set of complex numbers z1 bigger than z2 or z1 less than z2 are meaningless, but absolute of z1 bigger than absolute of z2 or absolute of z1 less than absolute z2 are meaningful because absolute z1 and absolute z2 are the real number. So we have 1 absolute of z will equals to 0 when z is equals to 0. In example, the real part of z is 0 and the imaginary part of z is also 0. Number 2, z absolute is equal to z bar absolute and also equals to minus z absolute. Number 3, the real part is bigger than equals to minus z absolute, and the less than equals to z absolute, and the imaginary part also bigger than equals to minus z absolute and less than equals to z absolute. Number 4, z times z bar is equals to z absolute square, and z absolute square is equals to z bar absolute square. Number 5, z1 times z2 absolute is equals to z1 absolute times z2 absolute, and z1 over z2 absolute equals to z1 absolute over z2 absolute, where z2 is not a zero. Number 6, z1 plus z2 absolute square equals to z1 absolute square plus z2 absolute square plus 2 times reals of z1 times z2 bar, and z1 minus z2 absolute square equals to z1 absolute square plus z2 absolute square minus 2 times real of z1 and z2 bar. Number 8, z1 plus z2 absolute is less than equals to z1 absolute plus z2 absolute. Number 9, z1 minus z2 absolute is bigger than equals to z1 absolute minus z2 absolute. And number 10, a times z1 minus b times z2 absolute square plus b z1 minus a z2 absolute square equals to a square plus b square times z1 absolute square plus z2 absolute square. And in particular, z1 minus z2 absolute square plus z1 plus z2 absolute square equals to 2 times z1 absolute square plus z2 absolute square. Number 11, z equals to a plus ib where not equals to 0 is 1 over z equals to a minus ib over a square plus b square equals to z bar over z absolute square. The representation of complex number as points in the plane is called the Argand diagram. So the two complex number of z1 and z2 represent by point p and q, and let's say that absolute z1 minus z2 equals to pq. We can plot each point like below. So here is the real part and there is the imaginary part. Then we just put any coordinate which is given by the z1 and z2. Maybe it can be here or there. We also can represent a polar form of a complex number. Let p be a point represent a non-zero and z equals to a plus ib in the Argand plane. If QP makes an angle theta with the positive direction of x exists, then z now equals to r in the bracket of cos theta plus I sin theta. And this is a polar form of the complex number, where r equals to the absolute z equals to root of a square plus b square, and tan theta is b over a. Theta is the amplitude or argument of z, or can be rewritten as arg z equals to theta. The value of theta such that theta bigger than equals to minus pi and less than equals to pi is called the principal argument. So arg z1 times z2 equals to arg z1 plus arg z2, and arg z1 over z2 equals to arg z1 minus arg z2. So if we plot the polar form diagram, will look like this. Here is the arc of z, here is the z absolute, this is the imaginary part, and here is the real part. Also there is the z here. Example, evaluate 1 plus I power of 6 plus 1 minus I cubed. So the 1 plus I power of 6 equals to 1 plus I square power of 3, and this is equals to minus 8I, and 1 minus I cubed is equals to minus 2I. So the solution of our problem is minus 2 minus 10I. Another example, if the imaginary part of 2z plus 1 over iz plus 1 is minus 2, show that the locus or the root of the point represent z in the Argand plane is straight line. So to solve, let dz equals to x plus iy, then our equation become like this. And thus the imaginary part of 2z plus 1 over iz plus 2 equals to 2y minus 2y square minus 2x square minus x over 1 plus y square minus 2y plus x square. But in our problem, the imaginary part of 2z plus 1 over iz plus 1 equals to minus 2. So the result now is like this. And we know that this is a quadratic equation, so if we plot to the Argand plane, it's not straight line. So in an example of x plus 2y minus 2 equals to 0, this is the equation of a line. So if we plot this to the Argand plane, this will be straight line. Another example, suppose we have RLC series circuit below, and we need to calculate the inductive resistance and capacitive resistance, circuit of complex impedance, and also the power factor. So we know that R is 10 ohm and the inductive resistance XL is 2 pi times F times L equals to 47.13 ohm. And the capacitive resistance XC is 1 over 2 pi FC and got 31.83 ohm. And the complex impedance Z is root of R square plus XL minus XC square, and we got 18.3 ohm. And the power factor is cos theta, which is R over Z, and got 0.546. So the phase theta is 56.9 degree. Next, I'll show you the implementation of complex number in control system by using the Labview. First, we take the while loop and give the stop button. Then we take the transfer function block and the locus plot. Then we put the transfer function equation in here. In here we use the s plus 7 over s power of 4 plus 4s cubed plus 475s square plus 1500s. Then let's run this, and the graph will give the information of the root position, whether it's in the real part or in imaginary part. So let's move to the assignment. Suppose we have a parallel RLC circuit with the constant S given below. Then calculate the R, XL, XC, power factor, and the phase angle. So I think that's all for the complex number. See you on the next lesson, and thank you.